Suppose you have a pile of fair coins. As an experiment, suppose that every 6 minutes you flip all the coins simultaneously, then discard all the coins that landed heads. How long would it take before you exhausted all the coins? Since a coin could potentially land heads 1 billion times in a row, there's no upper limit to how long it would take to exhaust the pile. But since about half the coins will land heads and be discarded, we can predict that the size of the pile will be halved every 6 minutes. And this would be true no matter how big the pile was. Since after every 6 minutes, half the coins remain, we introduce the idea of the half-life. The half-life of a substance is the time it takes for half the substance to disappear. In this case, we'd say the half-life of the coins in this experiment is 6 minutes. So let x be the time until a coin is discarded. Can we find the probability that x is equal to some given value? Let's ignore the probability aspects for a moment. From previous courses, you know that this type of problem can be modeled using an exponential function. Given some initial amount a0, the amount after time t can be modeled using Now, in our model, all the coins are flipped simultaneously every 6 minutes. So there are 1,000 coins until 5 minutes and 59 seconds, and then at 6 minutes, about half of them are going to be discarded. What if they were discarded continuously, but still preserving this half-life of 6 minutes? And the advantage here is that once we have the mathematical function, we can model it by allowing our variable to be continuous. And we typically don't write our exponential functions in this form. Instead, we like to use the base e, so let's do a little bit of work here, and we find and this leads to the following idea. If a quantity is subject to exponential decay, we can model the amount remaining after time t by where a0 is the initial amount and lambda is some rate parameter. Let's convert this into a probability distribution. Note 2 important requirements. The coin only ever lands heads once, since after that it would be discarded, and the probability of landing heads never changes. The amount remaining after time t is a0 e to minus lambda t. By the frequentist viewpoint, the probability that something lasts that long will be, since this corresponds to the probability of something remaining after time t, this means our probability that x is greater than t is e to minus lambda t, and so the probability that x is less than or equal is 1 minus. And this leads to the exponential distribution, which is a continuous distribution with parameter lambda and cumulative distribution function. Consequently, its probability density function will be the derivative. For example, the half-life of a certain isotope is 8 days. What's the probability that an atom of the isotope will last for 10 days? Since the half-life is 8 days, this means the probability that an atom will decay within 8 days is 0.5. So 0.5, that's the probability that the lifetime is less than or equal to 8. This gives us an exponential distribution, where if we solve for lambda, we get Now, the event lasts for 10 days is complementary to decays in 10 days or less, and so we find